Thanks for the invitation. So I work in Expedia Group as machine learning scientist, and today I will be talking about how we learn representations and how we use them in hotel ranking. So why we want to do that is that the reason is very obvious, that we want to be able to have meaningful similarities between properties. In our case, you have hotels, you have vacation rentals, you have when you go on our website, right, and you want to book something, or in any of the websites of Expedia. So we would like somehow to be able to represent properties in with a vector, with a dense vector, and be able to extract meaningful similarities. And why we cannot do it easily with standard techniques, like, for example, you could extract features with amenities and other features like star rating and compare them, is that it's not easy to compare this kind of representations to and having some similarities. So this work that I will present is published recently in a workshop in Rexis. If you want, you can check the exact material. And so the main idea here is that we use search click sessions, right? So you go on the site, you search for a certain destination, like, for example, you want to go to Paris, and you start clicking in hotels, right? So in this, as I represent here in the left figure, creates a session of the user, right? So you click in hotel 1, hotel 2, 3, 4, and 5, etc. So we want to leverage this information to learn representations, and these are basically ideas and how we do it, and already explored in other works also in other settings. Is the equivalent is in documents, right, in text. So we have sequence of words, and we would like to learn meaningful similarities for the words, right? And you all know of Word2Vec, which is a seminal work on the NLP community about learning distributed representations. So the idea here is the same, right? So when hotels that are clicked co-appear, I mean, they appear in the same sessions, then for us, this is a strong signal that these hotels should be similar. And there are multiple applications, right? You can see here in the different citations here. In other use cases like Pro2Vec, Node2Vec, that use the same idea on a graph, as well as Airbnb listing embeddings. So you can take a look into these works if you're interested. So what we propose here, and this is different of what other people have already proposed based on the same idea of Word2Vec, is that we complement basically the different information when we learn such a model. And I will explain later what type of model we learn, basically the loss function, etc. And if you see in the right figure, you have the architecture of the network. So here in the upper part of the figure, we have the click embedding. It's right. Is what you would normally learn if you would use just the simple way of learning in the similar manner like Word2Vec, right? So this is what we call click embedding. But apart from that, we add more information like amenities, star rating, gesture rating, and other features. So this complements the part on the input, plus geographical information. So we want to capture also some sense of geography in our embeddings, which is already captured by the click embedding. Of course, when you search and you search for a certain destination, you want to go to Paris, you go click properties in Paris, right? So you normally your vectors, when you learn them, they will capture this fact. But by adding extra information, we hope that we can do better. And the main reason of doing that is that if you can cope with the cold start problem, which means cold start is that when you have new, let's say, hotels arriving in the inventory of Expedia, we need to have a way to infer a vector, right? And as we don't have yet information on clicks, what we can do is we can just pass information on this lower part on amenities and what other information we dispose, plus geographical information, get it through the network, and get this enriched embedding, which we use as our representation. So this is the main idea, and you can see the operation is, so we have some normalization operations. We pass through some layers for non-linearities. We concatenate another projection, which gives us the enriched representation, which is what we use after all as a hotel representation. And then we predict against the full inventory. So as I told you, what we use as features is the clicked hotel, of course. So we use the embedding of the clicked hotel. We have amenity features like just rating if the property has a pool, if our pets allowed, spa, if there is any spa service, etc. So it gives us this vector, which we project down to 15 dimensions here. We also add geographical features. We have some encoders, a specific one which is called space to vec, which takes lat long and calculates basically it's a concatenation of multi-scale representations, plus H3 embeddings. This is a hexagonal system that was proposed by Uber, where you can break down the whole world in hexagons. And basically, we use the idea of the hexagon that the hotel appears in. And this gives us, which we concatenate with space to vec, and we then project. And this gives us extra information on geography. So the way we train the model is we use the steepgram model, right, like port to vec, and we use negative sampling for the loss function, right? So we have a first term of the steepgram pairs, like input output. So the hotel that is the target, and what we want to predict is the context, right? And I will explain you how we calculate these pairs. And this we want this to be similar, right? Because they're co-clicked, plus a term that where we sample negative examples, and we want this to be dissimilar, basically, if you see the formula, right? And the way we do negative sampling is very specific to the use case, because when people search on our sites on Expedia, they will search for a certain destination, like Paris, like Athens, and they will co-click in the same market. So in order to have more, let's say, harder negatives, so better learning, so more robust representations, we sample within this market, and we tell the model that this negative samples, this should be dissimilar with the target one. And this helps a lot in learning better representations, because you can think that if I would just sample from any other market in the world, it's very hard to find co-clicks across destinations, which we can have. It's an easier task, so we make it much harder for the model. And the way to generate the input data, apart from the data that I showed you on amenities and geographical information, is that the pairs we generate is that we use the same manner as in the steepgram model. We have a window of, for example, here it was a window of 2, and then we create pairs. So we have a target hotel, and we create different pairs like H1 with H2, H1 with H3, and then we slide the window, and we create more and more pairs. So to train this model, we basically used around 65 million click sessions from users. This represented 1.4 million unique hotels. So what this means is that when we score at the end of the model, and we want to get, so we have a target hotel in the input, and we want to get basically, let's say, a score for all the whole inventory, we score against this 1.4 million properties, right? So you can think that it's not an easy task, right? So you should have a very large number of, let's say, labels. We have an average number of 6 clicks per user session, with a minimum of 2 and maximum of 50. We did some pre-processing here, of course, to clean our data. And how we train the model and compare the different baselines is that we split in with 80, 10, and 10% for training, validation, test, and we train with TensorFlow basically. And we do some search in the space of hyperparameters like learning rate, the embedding dimension. Here I just we have with both typeface the best values. Batch size, for optimization we select AZD finally, and for the negative examples we found the best was 2000. So in our first experimental part, basically we compare against some baselines, which are like the highest rated, the most popular. Highest rated is based on the guest rating, right? The most popular hotel last year based on bookings, and the most popular based on the for last week. And what I call session 32 basically is the model that uses only the click information, if you want, right? So this part of the model, it doesn't use the amenities or the geo information. And the way we do our validation here is that we evaluate is based on the context prediction, which we applied across our full inventory, right? So we predict for all these 1.4 million properties. And the metrics we present is one is it's called hits at K, and the different cutoffs for K for 10 and 100, and which basically we count how many times when we rank across the full inventory, all the scores that we get for the input hotel, how many times the context appears in the top 10 when you rank by this score, or in the top 100 properties. And then the mean reciprocal rank is basically you accumulate the reciprocal. It's basically a ranking measure, right? So if you rank the property that was co-clicked with the input property in the model at the first position, you get 1. If you rank it in the second position, you get 1 divided by 2, and so on and so forth. All right, and we calculate this also in for 10 and 100 for K for the cutoffs. And basically, you can see that by having the full information, like plus amenities plus geographical information, that we can obtain the best result for all the metrics, which makes sense. You see here, when we remove the geographical information, we drop a bit, and then when we just use the click information, we have even a bigger drop. And you can see that you can see the similar basically when you compare within the market. So when you restrict the evaluation, not across the whole inventory, but then we just calculate only for the same market. And this is how we can basically use also these baselines, most popular, etc. So what you can see already that even popularity, which plays a role, it's already gives a good baseline, but then it's not enough to have a good predictions, right? In the next set of experiments, what we did is that we wanted to evaluate the quality of the embeddings we were learning against other methods. So we compared against 2 graph methods. One is called GraphSage, and the other is called Cleora. Cleora basically doesn't really learn; it's more you do random projections. But it's quite strong competitor. if you want, as an approach. And again, with only the click embedding and then hotel to vec plus matrix factorization. Basically, here what we did is that we followed basically, let's say, glove approach, right? In the sense that we calculate the cocherence matrix based on the same window as we did for hotel to vec, and then we factorize this matrix. We use the alternate least squares to do that. We factorize this matrix, and this gives us embeddings for the hotels. And you can already see that this gives a quite good result for in our evaluation set. What is interesting to see is that approaches like GraphSage, they fail basically. What we found out from our experience to scale to this kind of problems. So the hits at 100, which is the metric will look often, it's quite low with respect to other approaches. And you can see that Cleora, which is another graph approach, it gets quite good metrics, while matrix factorization is also a very strong baseline. But you can see here again that it's meaningful. I mean, the model learns some meaningful representations, right? We're close to what we were seeing previously in the previous set of experiments. And our final set of experiments was to do cold start, so which means that our setting was we had an out-of-time test set where we had new properties that arrived on the inventory of Expedia, and we imputed them with different ways for the different methods that we compared. And then we had a test set where the input property in the model was always basically a new property, and we want to see if we can predict well for these cold start properties. So in our case, basically, we would impute via our model, while for these approaches, we would use some proximity to average based on the embeddings we get for each approach, based on geographical proximity. So we take top 100 similar hotel embeddings within the market. And you can see that by just using the model, we can obtain better hits at K and MRR at K for against all the other methods, right? So that was quite interesting experiment. And before jumping to A/B test results, let me share you a quick demo and see how this looks like basically when we do some visualization. So here, for example, you can see that I select the hotel. This is Hyatt Place in San Francisco, downtown. It has a star rating of 3, just rating of 4.1. And the price is around 254. This is an average price. And you see here that there is the most similar properties. And if you compare against different dimensions like guest review rating, the price, star rating, and room count, you can see that it makes sense, right? They are quite similar, especially for guest review rating, very close for price, very close range for star rating, plus also room count, right? Most of them are big hotels. And if you can see also the placement, so this is our reference hotel, all of them are downtown, right? So they're very close, and this makes sense, right? Because when you want, for example, you want to visit downtown or a certain destination, you have already kind of an idea, so you start exploring certain neighborhoods, and this is basically captured already in the embedding space. So then what I did here is that I project this embedding space using UMAP. So I just project in 2 dimensions to be able to visualize. And then I plot against different dimensions like star rating, just rating, and price. And basically what you can see is that, go down, you have here a part that I will explain you why this is white. So here you can see it's not very clear here. We have to zoom in that you have some parts with lower star rate, just rating, and some parts that are higher just rating, and then it's similar. You use the the star rating. For example, here you have a cluster of 2-star rating, or here it's a mix, right? It's always a range, but you can see clearly that there is a separation. So here it's better star rating hotels, and similar it's for the price. Then in the lower part, basically what I did, I removed the vacation rentals. Vacation rentals are it's homes, right? It's apartments, so they're not regular hotels. So what you saw here, which is they fall all together, it's this blob basically are vacation rentals. So when I filter them out, they disappear, right? And this basically shows us that the model also can capture information on the property type, right? Which makes sense. So usually, for example, if you like boutique hotels, you will start completing boutique hotels. And similar for the price, we can see here is more clear that we have a difference of price, and there are hotels here, for example, that are more expensive. And then if I want to, I have one more example. It will take a few seconds to run. So I think this is from Paris. And we will see how it looks like. So this is yes. Yeah, this is from Paris, right? You can see that it's a 3-star rating, 3.6 just rating. It's quite close in price, star rating, and in terms of geography, I mean, it makes sense, right? All of them are very close. So you can see that we really can capture these similarities, and then waiting a bit to load these vectors, but you can see that they are very close, basically. Maybe you're interested to go in certain to visit certain areas in Paris, right? And we can. It's very nice that it can capture also kind of the property, because here, apart from these two, you have a lot of them that are very few rooms, right? So there are more kind of, let's say, boutique hotels. And here is projection. Here we have a lot of big inventory, of course. So you can see here, for example, again, there's a big part of it is a lot of VRs, right? You can see that we capture well this property type. So all of this part here is removed. Okay, good. Let me go back to the results. So then, well, what we did is that basically we run a online test. So we have a ranking model that uses certain uses context, right, and search features, property features. Like price, ratings, geographic information, and other things. The search features is, destination, which days you want to travel, how many travelers. So we have it's a learning to rank model. And what we did is that we test this model with the different embeddings we have. And our first test is that we compare our champion model with using property embeddings with our initial, let's say, a version of vectors, was the matrix factorization vectors, the ones that I showed you previously, right? Where you calculate the covariance and then you use ALS to factorize this matrix. And this is our first test. And in the second test, this was a sequence of tests. We used the hotel to vector representations, which we plugged in as features in our learning to rank model. And these are the results. So in the first test, what we observed is that we had a neutral conversion rate. So there is no impact in conversion rate using this model, the variant, while we had a positive impact on gross profit. And what we found out from this test is that the click embedding was capturing some, because it captures price, it was maybe capturing a lot of aspirational, aspirational clicks, right? So it's behavior in the sense that it favored more expensive rankings, but in the same time with high quality hotels. So if you could see the top rankings on our engine, you could see that it was a bit more expensive, but without impacting conversion rate. So this would mean that we don't impact conversion rate, but we are able to propose better quality hotels, which may be more expensive. And sometimes, if you think about it, when you go click, for example, properties, hotels, you may click hotels that you will not necessarily book these hotels. It would be more to see how they look like, right? And sometimes you may click very expensive hotels. So we think that this is kind of was captured in these vectors. While in the second test, this was quite interesting, is we had the inverse, right? So we had the positive conversion rate, while the cost, in terms of gross profit, it was neutral. And as we saw in the back testing results, it captures better the similarities, and it had a better way of imputing for new properties, and this is why we had this result. So we still work on this model. There are kind of a lot of current and future work. So, for example, how you can ensure when you do online updates, for example, of the model that you don't have any drift on your vectors, that can be used in other downstream tasks, as we did for the search, for hotel search, and also add more information in the model, right? So learn directly the type of property, be more dynamic by adding pricing, more amenities, even more geographical information. And that's all. I think I finished here, and let me know if you have any questions.
Thank you, Ioannis, for your presentation. The first question from Mihal: how did you deal with popularity bias within your model? How did you mitigate the problem of the most popular hotels dominating your predictions?
Yeah, so that's correct. So for now, what's happening is that if you use, let's say, and this we can see it here, the most popular already captures is quite strong, and for now we don't deal with it. We don't take any action on it. So we depend on right on the ranking engine. So which means that if we are basically biased towards more popular, we'll show more popular. Co-clicks will capture that, right? And we could see that maybe in some cases, in some markets with less popular, we're not able to predict well. But what we found out is that the model, it can generalize as well, even though we have some thoughts of how to mitigate this problem. But for now, as it doesn't impact any of our downstream tasks, we didn't consider in the first version of this model. But yes, it's in our plan of solving this problem.
Mm-hmm. We're running out of time, so maybe one more question. How exactly do you choose negative examples, as there are more negatives compared to the size of a batch size? Do you use the whole inventory for obtaining negatives? Also, are negatives filtered by geolocation or just the hardest one?
So yeah, so we use, as I explained, we do by location, by the market. So for example, we are in Paris, then we select negatives from Paris only. So we'll not select from. So we blend different regions, but we select from the market negatives, and we just use the geographical information. And this we found out that it's quite strong. It gives quite strong improvement and in the quality of the embeddings.
Mm-hmm. Thank you for your answers. Unfortunately, we ran out of time. Would you like to add something?
Me?
Yeah.
Yeah, it was a pleasure to talk to this conference, and if people are interested, please reach out to me for this work or any other work. And yes, also we also hire. So if you're also interested to see what we do in Expedia in terms of machine learning, just reach out to me. And for general research questions also, if you work on this in these areas. But thanks a lot. It was really a pleasure, and I like this dynamism you have, and a very nice panel of speakers, and I like the fact that you have this kind of applied aspect, which it's very important, right? So we see how all these approaches impact daily tasks, in different platforms, in different problems. So great job, and thanks.
Thank you.